Hi, I'm Bob. Welcome back to the tutorial on the exercises and applications for the textbook Econometric Analysis, the 8th edition by Professor William Greene. Today, we will find answers to exercises from 1 to 4 at the end of Chapter 4, estimating the regression models by least squares. Here is exercise 1. Suppose that we have two independent, unbiased estimators of the same parameter, theta, say theta1 hat and theta2 hat, with different variances v1 and v2. What linear combination is the minimum variance unbiased estimator of theta? For the linear combination, C1 times theta1 hat plus C2 times theta2 hat. Its expected value equals C1 plus C2 times theta1. Because theta hat is also an unbiased estimator, the sum of C1 and C2 must be 1. Next, we write the variance of theta hat. There are 3 terms. The last one is 0 because theta1 hat and theta2 hat are independent. We have the expression for the variance of theta hat. It is a function of C1, v1 and v2. The first order condition for minimization is the first derivative with respect to C1 equals 0. It leads to the answer. The weights C1 and C2 are functions of variances v1 and v2. The second order condition is satisfied. Therefore, the two weights C1 and C2 sum up to 1, and the weight ratio is the inverse of the variance ratio. Let's solve exercise 2. The simple regression has 0 conditional mean and constant variance. We will choose a linear estimator that has the smallest mean squared error. Suppose the linear estimator beta hat equals C prime times y, where C prime is a row vector function of x. We can compute the expected value of beta hat. The first term is C prime times x, because C is a function of x. The second term is 0, by the 0 conditional mean assumption. So we have equation 1. Then we compute the variance of beta hat, which is equation 2. With these two elements of the mean square error in hand, we obtain the mean square error in terms of C, sigma, beta, and x. The first order condition for minimization is the first derivative with respect to C equals 0. Using the vector derivative rules and the fact that the transpose of a scalar is itself, we get the answer. In part B, we plug in the expression of C to find the mean squared error of beta hat. Note that C is a column vector and C prime is a row vector. Then we write down the mean square error of the OLS estimator B. It is just its variance because it is an unbiased estimator of beta. Finally, we compute the ratio of the two mean square errors. As tau approaches infinity, the ratio approaches 1. Let's turn to exercise 3. Suppose the true model is y equals beta times x plus epsilon. There's no constant term. But we specify a regression with a constant term. The least squares estimator of the slope parameter beta is b. We write b in terms of x, y, and m0. m0 is the residual maker for the constant term. Using algebra, we can show that the variance of b equals sigma squared divided by x prime times m0 times x. Sigma squared is the variance of the error term. On the other hand, for the true model, the OLS estimator of beta is beta hat. We can also write its variance, sigma squared divided by x prime times x. We will compare the two variances. That is, to compare the two denominators. We can show that x prime times x is larger than x prime times m0 times x. Note that x prime times I is a scalar because x is a column vector in a simple regression model. So, the variance of the OLS slope estimator with an unnecessary constant term is larger than that without a constant if the true model does not have a constant term. Let's find answers to exercise 4. The disturbance has a positive conditional mean. We will show that the least squares slope estimator is unbiased, but the intercept estimator is biased. We can write the slope estimator in matrix form and then show that it is unbiased. But a simpler method is to rewrite the model as y equals pi plus beta times x plus mu, where mu has zero conditional mean. The OLS slope estimator B can be proved unbiased, while the intercept estimator is biased. Thank you so much for watching this video. See you soon in the following exercises. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.